Good morning, Math 142. Getting really close to the end of the quarter. You'll see that I've got the calendar brought up. You should be looking at that right now. We are right here on Thursday, the 29th. Happy Leap Day. It's our stolen time day for the year. I have decided to not try to cram in too much, and talking to a number of other teachers that dropped 9.3 and 9.4 out of the class. I felt justified in doing that to give us a nice smooth sail into the finish. Today, I'm going to introduce the 9.1 material. I'll be in touch next week to introduce 9.2, and then really allow us to totally focus on the last exam, which will cover topics 8 and 9.1 and 9.2. And so you see these dates coming up, the 12th of March, which is in a little under 3 weeks. The hard deadline for all homework, quiz, and reading assignments will come. That'll be midnight on that Tuesday. So if you're going to be asking for an extensions, I'll give those up to that day. But eventually, I'll just say I'll give anybody who asks for an extension, I'll just move it to that date and say that's the hard deadline. So make sure it's done by then. And then right after that, at 12:01 on Tuesday night, Wednesday morning, exam 2 will be open. And similar to last time, it'll be open all day Wednesday, all day Thursday, and close at 11:59 p.m. on Thursday night. That will allow me to do all the grading on the 15th, so you can get feedback. And then if you're interested in doing a redemption, you can get those to me over the weekend. I'll have times that'll be available online on Monday and Tuesday before those exam redemptions are due by 11:59 p.m. on that night of Tuesday. Just so you know, I'll be leaving campus at about 3 o'clock, so I'll be unavailable for help after that on that day. And similarly, on the hard deadline day, if you're getting in touch with me at 5 o'clock on the 12th, there's no guarantee that I'm gonna respond and give those extensions that late in the game. So the sooner the better. You let me know. All right, so that's what's coming up. I'm gonna switch my share here to so this is yesterday's agenda. This is what we did in class, kind of pointing out that this is the M. But I think you'll find 9.1 a nice refreshing break. It'll feel more familiar than the recent stuff has. And that's largely because it's really all about the equations and the behavior of ellipses, which are really just stretched out circles. So I'm going to start by talking about, in the very first section of this class, we were talking about circles, that something like this, where there's a circle centered at 4, -2. You can see the equation right up here, that if you'll remember, it is x minus h squared plus y minus k squared equals the radius squared. So that would tell us right here that our radius, or our center, would be at 4. And since there's a +2 instead of a minus, that would actually be minus -2. So that would really tell us that the center would be right here at 4, -2. That's our HK. And then that the radius of this would be the square root of 64, which is 8. And you can see that if you draw and count out the radius, that there's really a distance of 8 from the center to any edge of the circle. So I'm bringing this up because all these ideas are going to be identical for ellipses. I'm not going to use the word radius because there's not really a radius. We're going to talk about its 2 axes. And I added this, if you'll see this equation right here. I just wanted to point this out, that if I did in Desmos click that as available, it would graph right on top of the circle. Notice that equation can be derived by just simply starting with this one up here. If we just divided everything by 64, these two terms, the x minus 4 squared would be over 64, the y plus 2 squared would be over 64, and on the other side, we would just have 1. And I write that because this is actually the standard equation for an ellipse, and this happens to not be an ellipse because these numbers are the same. They're both 64. So let's look at a situation where they weren't. So here is right here, you'll notice this is an equation of an ellipse. So same format where we have h minus k squared. Oh, no, not h minus k squared. Hold on 1 second. I meant x minus h squared. Sorry for these. I know the last video had a very big pause like this, but that's okay. We'll be quick. Happens in class too. So this would be x minus h squared over, and I'm going to hold up on writing what that is for a second. I'll tell you why. Y minus k squared equals, and this is always equals 1. So far this should look a lot, very much like the equation of a circle. But notice we have the equation 9 here and 16 here. Because 16 is the larger of the two, I'm going to call that b squared. And since a is 9 is the smaller of the two, I'm going to call that a squared. But if the 16 was here, I would put the b squared under there, and you'll see why in a sec. So notice that what happens here is we've got our center that worked out kind of like we'd expect. We have -5 and -5, so we have a center at 5, 5, just like if this were a circle. And notice how this 9 appears is that this is called the minor axis. The horizontal axis is called the minor. And the way that shows up is just like we would see a radius of the square root of that number. We've got this distance of 3 between the center to the minor vertex on either side, a distance of 3 to the right and left. And we have a distance of 4 from the center to the major vertex. And you can see that in the 16, 4 squared is 16. So really imagine that just like a circle, except it has, instead of a radii, it has 2 axes, a major, a longer, and a minor, a shorter. And it shows up like that. I expect all this to be pretty straightforward for you all, like not a big leap. You're like, okay, you graph a few, you see why, you plot the points, it works out like that. The one concept in this that is going to be new is this idea of a focus. And you may have heard this before in terms of parabolas as well, that what this focus is essentially when things bounce from, imagine light or heat or something bouncing based on the curvature of this ellipse, no matter what angle it leaves that focus at, it would end up passing through the focus on the other side, which basically means things are concentrated at that moment. So oftentimes with physics and science equation, there's sort of significant happenings at these moments called the foci. But the thing you're going to have to figure out is, how do I figure out what that distance is, right? And you might have peeked and see that I graphed this and put them there. Notice that I added and subtracted the square root of 7 from along the major axis. So a couple things is the foci are always along the major axis. They're vertical in this case, but if there was a longer axis and a horizontal, then the foci would be on the horizontal axis. And the way to figure out where this lies is to sort of use these numbers. And it's rooted in the Pythagorean theorem, but it's a little annoying here that the terms used for this are the same as the Pythagorean theorem, but they don't work the same way. So if we call that distance c, and whatever the longer distance we have from the center to the major vertex, we call that b, and then whatever the short distance is, we call that a. It's always going to work out that these two, the length of that half minor vertex and the length of this distance from the center of the focus, the squares of those are always going to add up to the square of b. So it's a little annoying, like b almost acts like the hypotenuse, even though we're used to always calling c the hypotenuse. So in this case, because it's always going to work out that a squared plus c squared equals b squared. And in this case, b squared is 16. A squared is 9. So these two numbers will always be the two numbers you see in the equation of the ellipse. And the smaller one is always going to be added with c squared to give you b squared. So if you'll notice, if we subtract from either side that 9, you might see where that 7 came from. We get c squared equals 7. So c would have to be the square root of 7. So really that square root of 7 is about 2.6. So you can see that that's about 2.6 above, about 2.6 below. So just so you see what this might look like in a homework problem, it might look like this is the exact same one where it might say, what's the highest point on the major axes? Well, that would be this point right here. What's the lowest point? That would be this point right here. What's the rightmost point? Really, it's just asking us to name all the vertices. And then the highest focal point and the lowest focal point. And again, we just walked through all of that. So anyway, that's just one question, but in order to keep this video short, I'm not going to go over a bunch, but I am available on both Zoom office hours tomorrow or on the forum to respond to the things you struggle with as you come across. I will catch you soon. I hope you're all doing well.